Okay, so I want to talk to you all about better ways to capture CO2 from the atmosphere. So we've released 1,000 billion tons CO2 since we passed the threshold for the planet to be livable. And if we want to leave a recognizable planet to our kids, we need to do two things. We need to stop emitting CO2, and we need to remove all the excess, the historical emissions since we started emitting CO2. This is a mammoth scale problem, but it's also a mammoth opportunity. $50 a ton CO2, which is widely considered the target price for removal to be feasible, times 1,000 billion tons would be a $50 trillion cost. But who's going to pay $50 trillion to remove all of this carbon? So Chris and I think that the only way that historical emissions are going to be addressed is via international agreement between the world's governments. We think at some point, hopefully, the world's governments are going to come together to get this done. Though this is clearly a risk as to when this might happen, or even if. 1,000 billion tons means that many competing technologies will coexist, and the cheapest methods will be used first. But this is very difficult to scale up to this level. Like 1,000 billion tons is a huge amount, and if you were to try to remove it over 50 years, it'd be 20 billion tons per year. And as an example, if you were to look at growing crops, burning them for energy, capturing and sequestering the carbon, then that would use over 75% of all farmland on the planet if you were to try to scale this up. And similarly, if you look at sort of the process that Chris and I work with, which is capturing CO2 from the atmosphere and sequestering it, then that 20 billion tons would use over 100% of the global electrical production. So Chris and I, so it's really hard to not run out of land, water, or energy at this scale. And Chris and I have chosen to work with the problem here, specifically where you run out of energy, because we feel that we have some control over the limitations that we run into. So we can decrease the cost with better technology, and it's possible for the world to deploy more clean energy to run this. What would this look like? You can capture the CO2 in a plant here. You can capture it from the atmosphere, transport it to the sequestration site, compress it, and pump it underground to an underground reservoir. And the costs of this are around $10 a ton for sequestration, which is largely permitting, monitoring, and insurance, $8 a ton for compression. Transportation can be eliminated by siting the capture plant next to the sequestration site. And the capture cost is a huge range from around $100 to $250 a ton for what we think is currently happening in industry for this process. The minimum is around $9 a ton, and we would be aiming for around $30 a ton to be less than $50 a ton total price. But this is kind of the wrong way of thinking about it in terms of dollars. The sort of better way to think about it in terms of improving this is in terms of energy, because this is expensive because of energy costs. So if you're thinking in terms of energy, there's still theoretical minimum energy, and we want to get closer to that, as close to that as we can. So we can improve this by designing a better material, where better material can capture carbon at a lower energy cost per ton of CO2, or you can design a better process, where a better process would also be lower energy, or could also use energy from cheaper sources or from free sources in order to run the process. So as an example, existing companies in this space already use waste heat, and this is great for bootstrapping, but there's no way that this will scale, because there's no way that we have this much waste heat across the planet at this scale. But that's why Chris and I are interested in using an alternate source of energy, which would be to use natural energy cycles to drive the process. So either using like a temperature swing or a humidity swing, the differences between temperature between night and day, or humidity between night and day, or light-dark cycles, or even tidal cycles, or seasonal cycles. So Chris and I think there's space to improve both the material and the process of capturing CO2, but we don't have a better material yet. What we do have is technology that can rapidly evaluate materials and processes in parallel and search the space of what is possible. So we have this materials discovery pipeline, basically, where what this would look like at a high level is broad computational search across the widest possible selection of materials and processes, where we then slowly winnow the fields down until we end up with a few to do in-depth computational analysis on, and then that field gets winnowed down to experimental validation. And at the point where we can validate something experimentally as being better performing than what exists, we would intend to spin out a company. We are optimistic that this is possible because there's been an explosion of materials development in the last 20 years. So before 2000, there were fewer than 1,000 porous materials known, and now there are over 100,000 porous materials known. So that's 100x growth. So there's a much greater search space to explore if you're looking for materials for specific applications. We're also optimistic because we've used similar processes before to spin out two other companies, Numatech and Aeronix. And we've also partnered with the National Energy Lab to work with them on power plant CO2 capture. And we are currently working with the National Energy Lab on a subset of this whole problem for direct air capture having to do with a specific material class. So we think that finding an economically viable material and process for CO2 is one of the grand engineering challenges of the 21st century and is one of the most important. And so we've been really excited to sort of share what we're thinking about with all of you today and in the past. So that's officially the end of the pitch. And I think that's around 5 minutes, but I have some more that I wanted to talk about in terms of progress that we've made over the last month and what we've learned from the accelerator. So I wanted to briefly come back to this sort of this funnel here in terms of what our timeline looks like. So we plan to spend a couple years on computational work that's almost entirely computational, where we would start testing experimental ideas starting in 2022 to 2023. And we currently have grant funding until here. And so we feel like we're pretty well set up right now to solve the problems that we want to solve without running out of funding before we would be ready to go look for it. So we would think about spinning out a company around 2023 once we can demonstrate more advanced lab scale technology. And one of the things that we spent a lot of time thinking about in this accelerator, which was kind of our main goal for being here, is just trying to think through what the right form for this company would be, or if it's even a company. And because of the funding that we have right now, we feel that we have a couple of years to figure this out. So we don't have to really worry about it right now while we deal with the technology risk. But I wanted to share a couple of things that we learned that we think might be helpful to the other teams. So there's this quote here that VCs don't like policy risk because they can't do anything about it. And I think this is a really helpful thought in terms of trying to get funding for carbon capture, because ultimately, if you're trying to address historical emissions, then it's almost for sure policy risk. The world has to come together to do something about it. And from lots of our conversations with people who do work at VC firms here, we definitely heard different variations of this in our conversations. And at the same time, though, we know that Climeworks, a company in the direct air capture space, has also managed to achieve $100 million of total investment to date for doing direct air capture. So we don't think it's insurmountable, but there's definitely a point of view and a frame in terms of thinking about it that might have to be overcome in terms of demonstrating what the risk is or find people that are interested in that risk. And we've also thought about bootstrapping a lot in terms of would we want to bootstrap a solution? And we wanted to set out to solve historical emissions, and historical emissions are really difficult to bootstrap. We kind of don't think it's possible. If you turned all of the emitted CO2 into some sort of dense plastic-like material and you spread it out over the surface of the land on the planet, it would be over 2 meters tall. So it's a huge amount of stuff. And so there's not really a bootstrap solution or a way of commercializing this at this scale. So it's just something that we are going to think about over the next couple of years. We know that there are businesses that one could make out of this that might be smaller businesses that may be more easily fundable, but they're not necessarily going to solve the historical emissions problem. So we also spent a lot of time this month on doing analyses and putting together sort of alternate scenarios, and hopefully some of that showed in our pitch in terms of the data that we have. But we made a lot of progress there in terms of our thinking, which we found really helpful. We also had great conversations about like bottom up versus top down design and thinking about the problem in different ways. So really, we're just really grateful to be here. And I want to give a big thank you to Foresight and Lou and Allison and Marcia for putting it all together. And thanks to all the mentors. And I also just wanted to put the offer out that if anybody thinks that that we can help them in any of the other teams, then we'd be happy to assist them in the future, whether that is related to materials design or even software development, then I would be happy to talk to anybody else. It's been great to be here. And I'd like to have any questions.
Thank you so much, Paul. That was lovely. I'm going to stop sharing your screen if you don't mind.
Yes.
And I see a few virtual claps here in the audience. Thank you so, so much. Are there any questions from the mentors? If you have any questions, feel free to drop them in the chat or raise your hand via the feature or just speak. Any questions, comments from the mentors? Is there an open? Yes.
So one of the things I see is this is kind of like a sliding window problem, because as time moves forward, the impacts, right, of the increased greenhouse gases in the atmosphere become more and more untenable. So how, with this particular model that you're putting forward, how do you see the ability to, so sure, I have every confidence that you'll find materials, but commercializing those materials, finding the right partners, and making an impact, how do you think about that particular issue?
So Chris and I are obviously computationalists, but we also have done a lot of work with startups and businesses, and we're partnered with the National Energy Lab, which obviously thinks a lot about these problems in terms of evaluating them, and also with like the NETL is building a prototype test plant for this sort of problem where they can evaluate different air capture methods to put them on an even ground with one another for analysis. So we feel like we have a lot of inroads to the right people in terms of scaling something like this out. But there is a really big question here, because when we think about running a business for this, there's a few ways. There's one, you build all the plants yourself, which is like trying to invent a multi-trillion-dollar industry, a business from scratch, just without having done it before in your organization. And so that's a huge project. And then there's also licensing the technology to companies that have done it before, which could mean even partnering with fossil fuel companies or other large industrial organizations that have some of the skill necessary to do this. Or possibly even if some of the existing direct air capture companies get big in the time frame and we find better materials, then partnering with them or selling the material, licensing the material to them. So there's a lot of different options, but only one of them would involve building a bunch of plants ourselves. And that probably is the most difficult path.
Thank you so much. Any other questions? We still have a little over a minute. Go for it. Yes, Giovanni.
Yes. Thank you for your presentation. And of course, you know, from a science point of view, and especially material science, this, you know, that's a very interesting, of course, project to look for this kind of new materials. And from a science point of view, I'm you know, all with you. But I have a more practical question. If you consider the whole process till the end of actually capturing then and pumping the CO2 underground and so on, is a better material really the roadblock in this whole process right now?
I mean, personally, I think the roadblock is political. I think that if we had the right political situation here, then, and we had carbon markets, then we'd have it incentivized to solve all the problems. And really, before you do carbon capture, you want to decarbonize the power supply and you want to get to net zero with your economy in the first place. I kind of view direct air capture, capturing CO2 from the atmosphere as the corrective, the only corrective we have for failing to make the right policy decisions 10, 20 years ago. So, and we're not making them yet either. So at some point, we're going to have to decarbonize the power supply and get there, but we're still going to have to deal with being way above the limits in what we want in the atmosphere. And so we're going to need something like this in order to make the planet back to where we want it to be.
If I could just chime in with one comment that sort of addresses your question, Giovanni, and a little bit touches on Tom Chi's point. To clarify, we're not necessarily, the outcome of our search process isn't necessarily, trying to design a new material that never existed before. There are, enormous libraries of porous materials and materials that could be used for carbon capture, some of which, may be vastly abundant, and we've been using them for other purposes for hundreds of years. On the very first call, I mentioned, dried vegetables as being porous materials. And it could be that some of these are basically solutions lying in front of us that just no one has thought of using for direct air capture because there's just, the ability to quickly evaluate everything that's out there is a challenging thing. So that's just to Giovanni's point. We're not necessarily saying that society needs a new material, but we do need to find a material that is, the most efficient when considering also that we need, thousands or millions of metric tons of it and all the other variables at the same time. I don't know, Paul, did you want to talk about our confidence for reducing the energy targets? Oh, maybe you could mention, what's known about the energy needed for carbon capture right now versus the theoretical minimum energy. If you want, or I could mention it.
No, but we did.
If you want to make it one sentence and then we wrap it out to the next project.
I know. So I think, Chris, what you were just asking was with the energy targets being like $30 per ton and how much energy, whether that's achievable. I figured that we have 2 years to see if we can achieve it, and then after that, we will either have net something like that or we won't have. And I think it's a search process that we'll either have a company or a material that's really valuable and interesting at that point, or we won't. And that's going to be making an interesting couple of years.
Fair enough. All right. Thanks.